Buenos días y buenas tardes a todos. Es un placer estar aquí para presentar a uno de los cosmólogos más extraordinarios que hay en estos momentos vivos. El profesor Andrei Linde, al quien conozco desde hace muchos años, fui postdoc con él en la Universidad de Stanford, es una de las personalidades de este área, de la cosmología. Nació en el año 1948 en Moscú y se doctoró en el año 75 por la Universidad de Moscú y estuvo allí hasta el año 89, en el que formó parte de la división de teoría del CERN, este laboratorio que todos habéis escuchado por estos resultados sobre el Higgs. Pues bien, estuvo en el CERN hasta que le invitaron a formar parte como catedrático de la Universidad de Stanford. Y allí se fue con su mujer, Renata Kalos, y hasta estos momentos está allí, en la Universidad de Stanford. Lo extraordinario del profesor Linde es que es uno de los padres de la idea de inflación, la cosmología inflacionaria. Junto con con Alan Guth, Andrei desarrolló la idea de inflación durante todos estos años. De hecho, ha sido el promotor de muchas de las ideas que en estos momentos asociamos con inflación. Realmente surgieron de él. Y es, sin duda, uno de los cosmólogos con más imaginación, como veréis, sin duda alguna, en esta conferencia, y mayor capacidad de transmitir imágenes, ideas, sobre ese universo primitivo que está muy lejos de nosotros, ocurrió hace mucho tiempo, y que, sin embargo, deja sus huellas, como él nos mostrará en muchos aspectos del universo actual que vemos. Ha tenido numerosos premios, y voy a citar algunos, que son quizá los más destacados. El premio Lomonosov de la Academia de Ciencias de la URSS en el año 78, hacía mucho tiempo. La medalla Oscar Klein de Física en el año 2001. La medalla Dirac por la idea de inflación, precisamente. Esta es una de las medallas más prestigiosas de la física teórica, en el año 2002. El premio Gruber de Cosmología del 2004 y, muy recientemente, el año pasado, fue elegido miembro de la Academia de Artes y Ciencias americana, el año 2011. Bueno, pues sin más dilación os paso la palabra a él para que nos ilustre sobre esta idea tan maravillosa, sobre el universo o el multiverso. Muchas gracias por vuestra atención.
Yeah, it works. So the subject which I'm going to discuss today is extremely complicated. I will try to do my best to make it simple. In an hour, it's very difficult, but it's morning in California, so I am full of strengths. Okay, so let's see. So the question is, why multiverse? And this idea of multiverse, inflationary multiverse, in fact, was proposed about 30 years ago. So the question is, why there is so much interest in it now? In fact, about 10 years ago, there was still no interest. Those who were interested in the theory of multiverse, they were considered almost crackpots. You know what crackpot is? It's a little bit, yeah. Well, approximately 10 years ago, something changed. And so what I'm going to tell you, what was 30 years ago, when all of these ideas start being developing, and what happened 10 years ago, which made them popular. So first of all, let's go explain historically. Historically, the question was, why universe? What we see when we look at the sky, we see the universe which is approximately the same to the right of us and to the left of us. So there was a question why the universe is so uniform, and inflationary theory, which is the theory which I was one of those who developed, inflationary theory explained why the universe which we see is uniform, and I will tell you how, okay? But then the same theory predicted that at a much, much larger scale, it must be extremely non-uniform. So, that is how inflationary universe, which was originally the way to explain why the universe is uniform, why it is homogeneous, isotropic, everywhere the same set of ideas, when we developed them a little bit further, they predicted that it is locally uniform, but at a much larger scale, it's very non-uniform. It becomes a multiverse. First, some pictures which you can find in the textbook even now. Okay, so this is the universe, this is the size of it. Or, if you wish, it is the distance between different galaxies. When the universe expands, the distance between galaxies grows. So when the universe was very, very young, the distance between galaxies was tiny, very small. And then the universe expanded, expanded, expanded. It can exist in many different versions. The universe may be closed, which is similar to the surface of a, well, football. You inflate football, it becomes larger and larger and larger. If the universe is closed, then eventually it may collapse and disappear. The universe may be flat, which means its geometry is similar to the geometry of a flat surface of table, so parallel lines do not intersect. They go parallel. On the surface of a sphere, what you seem to think about like a parallel lines, you have an equator, and you draw parallel lines, and they meet at the South Pole, and they diverge, and they meet at the North Pole, or vice versa, depending in which auditorium you are discussing it, North Pole, whatever. Okay, so if the universe is open means its density is not very large, it expands fast, then open and flat universe, both of them can expand forever. That's what we thought approximately, until 98. And in 98, experiments have shown us that actually the universe is accelerating independently, whether it's closed or flat or open, it is accelerating, it is not going to collapse. We just did not know that the universe has some very, very strange property, which is, well, empty space has a little bit of energy in it, which is called dark energy or cosmological constant, depending on with whom you are talking about it. The very thing is very strange. How is it empty and nevertheless it has some energy? Well, I can explain you. It would take a little bit of time. I will probably go to this later. But the fact is that, yes, this is something for which people deserve to get the Nobel Prize in physics, and that is discovery of acceleration of the universe because empty space has a little bit of energy. So we will return to this later. Okay, so that is this part of the picture. Now is more or less established. This part became a part of the textbooks starting from the beginning of the century. So the previous century, these are three pictures, okay? The beginning of the century, actually starting from 98, but not everybody believed in 98 that this is correct part of the story. But now it is in the textbook. That's how our universe expands now. Then this is a part which I am going to describe. This is also a stage of acceleration of the universe, which happened when the universe was very, very young. Now universe kind of slowed down. Now it's old person was like a bit fat, a huge universe. When the universe was young, it also experienced this stage of exponential expansion, which is called inflation. And that is the part to which I contributed. So why inflationary theory was invented in general? Inflationary theory was invented because there were several different questions which were asked by many people somewhere in 70s, in the beginning of 80s. There were some questions which could seem almost metaphysical, but people asked them. So one of the questions, what was before the Big Bang? So, well, nobody knows. Is it a physical question? Maybe it is a metaphysical question because there was nothing before the universe happened. There was a singularity. But, you know, you feel uncomfortable with not knowing answer to this metaphysical question. Why is our universe so homogeneous? Why to the right of us and to the left of us, density of matter in the universe is almost the same? People tried to answer this question. One attempt was made by famous scientist Stephen Hawking somewhere in the beginning of 70s. He written a very, very mathematical paper and formulated his answer in very mathematical terms. Let me reproduce the answer so that you appreciate, okay? On the set of all universes, I don't even know how you translate it into Spanish because it's difficult for me even to pronounce it in English. On the set of all possible universes, the set of those universes which after expansion reproduce our uniform space has measure 0, okay? Which means it's just no way. Okay, that's the simple transition. No way you can just by chance reproduce our universe. Okay. Now, what is then the explanation why our universe is so uniform? And in the same paper Hawking have written, but in a typical universe would be so inhomogeneous, then people like we would be unable to live there and ask questions. That is why our universe is homogeneous, because we cannot live in an inhomogeneous universe. This is called Entropic Principle. Well, unfortunately, this answer doesn't explain why somebody created the universe which is homogeneous everywhere. For our own existence, it would be sufficient for the universe to be homogeneous in the vicinity of solar system. Solar system, everything is fine. Other galaxies, I do not care. So this was not really a convincing solution. Einstein, on his term, instead of answering this question, he invented something which is called Cosmological Principle. And Cosmological Principle said that the universe is homogeneous because it is a cosmological principle, that the universe must be homogeneous. That was not the solution, that was just stating that the universe must obey the law, it must be uniform. But then that's okay if you do not look at the universe, because it has inhomogeneities, it has galaxies. And without galaxies, which are, well, clumps of matter, our life cannot exist. So universe is homogeneous because there is a principle, but it actually not quite homogeneous. And usually I made a joke that people who take small bribes cannot be called men of principle. See, they make small bribes, nevertheless, they are not men of principle. And so I continued this joke. I say that some people who do not have good ideas, they sometimes have principles. And then I stopped making this joke after I learned that this idea was proposed by Albert Einstein. So we needed to explain why our universe is so uniform. And there are some other parts. Why the universe is isotropic, means look the same in this direction and in this direction. Like a sphere, not like a cucumber. Okay? So why the universe is isotropic? Why all of its parts start expanding simultaneously? Who gave a signal? Because this part and that part, they did not know about each other when the universe was young. They did not have a time to tell, hello, let's start expanding simultaneously, because it takes some time for the signal to travel, and the universe was very young. So when I was a student, I thought that when I'm going to grow up, I go to the university and I find the answer to this question. I will ask my professors, and my professor will explain me why the universe starts expanding simultaneously. But when I went to the university, I found that the professors did not know that the question exists. So it was necessary to find explanation. And there were some other questions, like why parallel lines do not intersect. There is even a very, very silly question, which is actually very deep. Why there are so many people in this auditorium? Okay? Well, we have heard that there is a lecture. We decided to come. Why there are so many people in Madrid? Where there's a big city? Why there are so many people on the Earth? Actually, Earth is just one of the many planets in the solar system, and there are many other planets, and in other planets there are many, many other people. Why there are so many planets? Oh, look, in our galaxy, there are like 100 billions of stars. Some of these stars have planets, some of the planets have people, some of the people live in Madrid, and some come to the lecture. Why there are so many stars in the galaxy? Don't worry, we have so many galaxies. There are 100 billions of galaxies in the part of the universe which we observe. Why is then the universe is so big? And the answer is that, silly question, because it's the universe. Okay. So that's how it works. So in the end, just angry father say his child, just shut up. The universe is big, period. But what the problem is that when we start thinking about it, we start thinking where this mass of the universe came from. Because the total mass of the universe, if you just, recalculate it back in time, now the universe is heavy. But what happened, the universe in his childhood, unlike human children, they grow up, their mass increases. Okay? When, however, you go back to the origin of the universe, when it was born, for some special reasons, in the standard Big Bang theory, it must be much heavier than what we see right now. That's because when the universe was expanding, it loses some energy. It makes itself big and it loses some energy, and therefore it becomes less massive. Mass and energy, according to Einstein, this is the same. So when the universe expands, it loses some energy for expanding, it becomes lighter. Nevertheless, it's right now heavy. So in the early universe, the total mass of the universe must be 10 to the degree 80 kilogram. It's just a billion of 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 a billion kilograms. Okay? So who gave you this present? Because when the universe was born, we think that it's easy to create something when it is small, but now the baby must be born with the mass 10 to the 80 kilograms. And it must be done almost instantly and very, very homogeneously everywhere. When you calculate the size of the part of the universe back in time, you will see that it was tiny, tiny ball, maybe of a size about 1 centimeter, and then it must be ignited, exploded simultaneously in all of its parts with accuracy better than 1 in 10,000. So it's like hundreds of a percent accurate, uniform universe with this mass. Who gave you this mass? So the standard, not the textbook, but religious explanation. Yeah, we know who did it, because in normal physics, it's just impossible, so it's a miracle. And therefore, let's just attribute it to a miracle, so that's how the universe was born. Physicists are trying to do better than miracle. And what we did not quite solve the problem. We did not know what happened in the very beginning. We have some hypotheses, but we simplified the problem. We know how to create all of the universe and much more. And what I mean by much more, they start the process of creation of infinite number of universes from less than 1 milligram of matter. Okay? So if anybody would tell me this 30 years ago, that means before the inflationary theory was invented, I would tell this person, then go home and return to me next morning when you're not drunk. But because this is my result, I cannot tell this anymore. So this is how it works. Now, as I said, I will try to make it as simple as it is possible, but I cannot avoid introducing a concept of scalar field. Okay? So that's a necessary evil, but I will try to also make it as simple as possible. You have 220 volt in the socket. Yeah, electricity, 220. So all over Spain, you have 220. But all over Spain, you have 220 and 0 also. So if you have 220 and 0, you have electricity. I know it experimentally. We have 220 in Russia. So when I was a child, I put something here on my hand, and I still have a mark. So I know that 220 is really something, but this is a difference of potential. It hurts. If you would have 220 non-zero, but 220 all over Spain, but no zero, there would be no electricity, you would not know what voltage is. It would be just like a vacuum state number. In the United States, where I live right now, we have 110 volts. If we would have 110 volts all over the United States, you would not feel it. You would not have any difference in feeling whether you live in Spain or whether you live in the United States. But if you touch by one of your hands United States and another hand Spain, you will be dead, okay? Because there will be difference in potential. Did you see the birds sitting on high voltage lines? These 10,000 volts, okay? They do not care. They stay there on these high voltage lines and they are quite happy. Have you ever seen birds which have one arm on 10,000 volt, another on a different wire? No, they got fired. They evolutionarily disappeared because they just got dead. So they see so the message is the amplitude does not really matter. It's just like another vacuum state. So the scale field is very similar to this potential in the wall. If it is everywhere the same, if it does not changing, you move from one place to another, you wait a little bit, it remains the same, then it will be just another vacuum state. The difference between voltage in the circuit and the scalar field is that if it is large, then it has also energy, okay? And this energy contributes to the speed of expansion of the universe. When the field has lots of energy, the universe expands fast. But here, see, this is like potential energy. So this potential energy is very similar to energy of a pendulum. If you have a pendulum in the equilibrium position has no potential energy, or we may call it zero, okay? Then pendulum moves like that, and it has energy. And in the first approximation, it just quadratically depends on the distance from the equilibrium. So the distance grows 2 times, energy grows approximately 4 times. In the simplest models of scalar field, the same is true. When the scalar field grows, energy grows. In this simple case, it's quadratic. So phi is the scalar field, m is some parameter which has a meaning of mass of this field. Okay, so usually what you know about pendulum, when it goes from the equilibrium, it starts oscillating. That's what we expected about scalar field. What happened was actually more complicated. When the scalar field is large, then it moves down very, very slowly for the reason which I will explain right now. When it goes down, eventually it starts oscillating. But here, it almost sticks to the wall. So let me forgive me, there will be some equations. I'm not going to solve them. I'm going to point at them, okay? So this is slightly simplified Einstein equation, which tells you that the speed of expansion of the universe, this is like velocity, divided by its size squared, which is called Hubble constant, okay? So this Hubble constant is proportional to energy of the scalar field. When the energy was large, Hubble constant was large. That is, Einstein equation. This is equation of motion for the scalar field. Forget about this term a little bit. This is something which is called acceleration of scalar field. So if scalar field moves with a faster and faster speed, there is an equation which tells you this is how it is related to the value of the field. Large field, large acceleration, usually. This is an unusual term which appears when you take into account that the universe is curved. So this means simultaneously, I cannot easily explain its origin, but my colleagues would, grab me on my hand and say, you're cheating, if it were incorrect. So you write down your normal equations for the scalar field, and then you take into account that your universe is curved according to Einstein theory. Okay? Now, this is equation for the harmonic oscillator or for the pendulum falling down. This is acceleration of harmonic oscillator. This is returning force, which tends to return it down to the minimum. And this is the term which is called viscosity or something like that. This is the term if you put your pendulum into viscous liquid. Instead of oscillating like that, it will move down very, very slowly. So here is the idea of inflation. You start with very large value of the field phi. If phi is very large, Hubble constant is very large. If Hubble constant is very large, you have a system with very large viscosity. And therefore, scalar field phi moves down very, very slowly, which means for a long time it remains almost at the same height because it moves down slowly. If this field is almost constant, write constant in this equation just to feel what it is going to happen. If you write down this constant, this is the simplest possible differential equation. There is impossible to cheat here. It just, you start your education of your student by showing them an equation like that, a dot divided by a is equal constant, and they know what the solution is. The solution is exponential expansion of the universe. So it's very, very simple. So once again, let us go back here. We must start with sufficiently large value of the field phi. If this is large, then this ball moves down like a pendulum in a viscous liquid. For a long time, it stays here. And then it very, very slowly goes down. During this time, our universe expands exponentially. Okay? When the field goes down to the minimum, friction term becomes small, it starts oscillating like normal pendulum, and then it creates particles. And these elementary particles, by these oscillations. And these elementary particles, they interact with each other. And while they interact, they make the universe hot. And we were working on the theory for quite a long time together with Juan Garcia Bellido, who introduced me today. So we know how to make the universe hot. But this is like what happened after. What happened during inflation is that you may start with a tiny universe, and then rapidly it becomes very, very large. How large is large? These are the numbers. You start with tiny, tiny something, and suddenly it grows by this amount of times. And that's just incredible. And once again, as I said, if somebody else would tell it to me, if I would not be solving equations, I would say, but that's impossible. We never have numbers like that in physics. You have 100, a million. You may even have Google. Is it Google like 10 to the degree 100? So people who invented this Google company, they used this 10 to the degree 100 as the largest number possible. Well, they just did not know that the numbers like that exist. Now, how do then you start with the universe? Let's start with something tiny, 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 like, this is the smallest size which you can describe in quantum theory of gravity, because if you start with something smaller than that, quantum fluctuations of space-time, they become shaking, all of your rulers are bending, all of your clocks start winding, unwinding. So this is smallest as you can go. And this part of the universe have a very tiny mass, which is approximately, 10 to the minus 5 grams, almost nothing. Then after that, you wait a little. How little is little? You wait 1 billionth of a billionth of a billionth of a second. Practically nothing. After that, the universe becomes like that, this size. And it is in any units of length, in miles, in centimeters, in kilometers, in whatever, it really does not matter. That's how big it is. So why then the universe, why parallel lines do not intersect? Well, think about our Earth. And if our Earth would be that large, then you would never go to the South Pole. You will be always moving near the equator. So you would think that parallel lines, they must be parallel. So the distance from the South and the North Pole will be given by this number. That's why nobody sees parallel lines intersecting. Why the universe is so large? I gave you in the beginning the number, which was huge, 10 to the degree 80 kilograms, okay? That's how much we have now, easy, from 1 milligram. You want a miracle, we give you the miracle. But now we have equations which explain how this miracle happened. Okay, so this is the first part. This is how you make universe. Because if we start with the universe, which is red, and that's how I started, I came from Russia, so we have a huge red universe everywhere. Now, when I am living here, though, I see only this part of the huge universe. Why do I know that it was all red to start with? So let us go to the, oh yeah, that's another picture. You see, everything is red. That was in Russia. But in the United States, it was no better than that. That's the famous sentence belonging to Henry Ford. Any customer can have a car painted any color that he wants as long as it is black. So it's red, and then everywhere red. Oh, it's a color of car, and all these Ford models, they were originally black. So now, here comes the multiverse. And that is a concept which is dear to the hearts of many people sitting here. So let's start with the football. Or making it more interesting, let's start with multicolored football. Okay? So now suppose that I was here in the red, and you were here in the blue, and then after inflation, you have it, here I am, and I do not know even that you exist, because the distance from here to here is this 10 to the degree whatever it is, okay? So then, how do you know that this is not a true picture of the world? Well, what Einstein knew, he knew that the universe is everywhere the same, because what we can see, the largest part of the universe which we can see, is only 10 to the degree 28 centimeters, which is 10 billion light years. This is the distance light propagates during a lifetime of the universe. So that's what we see. This is minuscule as compared to the size of the inflationary universe. So this means that we actually do not have any experimental facts which would explain this hypothesis that the universe is everywhere red. So then we can take the different perspective, which I call Cosmopolitan Perspective. Why not this? Why not multicolored universe? Now, this is not the full picture, but here you have 2 points of view. First point of view is a pessimist point of view, and pessimist will tell you, if each part of the universe, multiverse, is so large, we will never see its other parts, and therefore it's impossible to prove that we live in a multiverse, right? So what I'm talking about right now cannot be proven. So I'm talking about, well, this fancy hypothesis. Now, optimist will tell you something different. He will tell, in each part of, if each part of the multiverse, it is impossible to disprove this theory, okay? So now, it's the same argument, but it's vice versa. And the reason why I'm thinking about this argument in this way is that, look, you have one theory of electromagnetic interactions, and that's everything which, well, also nuclear physics. And from these basic laws of physics, you build all different people in the auditorium with all different shirts and, well, boots and everything. All of this is different. Now, if there will be somebody microscopic here, sitting here, he will think that every man must be white. Okay, but unless we prove that they must be white, then they can be whatever color. Okay? So now the burden of proof is on the shoulders of those who is trying to say that our universe must be single-colored. We must have a reason for it to be single-colored. Okay? So now let me go forward. So this scenario of the multiverse is more general. You in general say that, well, you start with whatever chaotic distribution of colors. And then this is our universe. Previously, we thought that we cannot start with chaotic distribution of colors because then the universe becomes big and still, well, different in different parts. That was what Hawking told us. Hawking told us that if we start with general inhomogeneous multicolored universe, you will always get inhomogeneous multicolored universe. But now inflation tells you that if you take just tiny island of homogeneity of a size which is the minuscule, 10 to the minus 33 centimeters, and after that you get inflation, you solve this Hawking's problem. You know how to make homogeneous part of the universe. That's it. So this problem is right now solved. And what is the next step? This would not be sufficiently general, nevertheless. For me, myself, I would not be quite happy. But what happened is that even if you start with the red universe, during inflation, it becomes multicolored. And that's something which I'm going to explain right now. So, until now, I was jumping from, well, cosmology, equation for scalar field. Now I'm going to jump into quantum mechanics. So this is an empty space, well, near me, so I think. And I think there are no particles there. Now, however, if I take a microscope and something, well, make one shot after another looking at what is going there, quantum mechanics tells me, you know this uncertainty principle. If you have very tiny period of time, delta t, you cannot really say that there is no energy at this time because there is an uncertainty relation, delta t, the length of the time interval, multiplied by delta energy, the uncertainty of what is energy here, must be larger than some constant, which is Planck constant. Okay? So when we take a microscope and we quickly look at what is in the vacuum, there will be always some quantum fluctuations appearing, disappearing. They cannot be forbidden. But when we look at this on our human scale, like minutes and hours, then this delta t becomes very large, delta E becomes very small, and so you can ignore in normal life, you can ignore these quantum fluctuations. However, during inflation, these tiny quantum fluctuations, they suddenly become large. So you start with something tiny, and during a short time the universe had, suddenly this thing becomes exponentially large. So that's what happens. These original fluctuations suddenly become large, and because of these terms, 3h phi dot, because of this viscosity term, it expands and then it freezes. It's like that. Okay, it becomes inhomogeneous distribution of scalar field phi, and it stretches. And on top of these, other quantum fluctuations freeze and stretch, freeze and stretch, freeze and stretch. So what we get inhomogeneous distribution of the scalar field. And you know what? When you cannot really explain it in depth, what you do computer simulation. So this is a computer simulation of what happens in the early universe. Each moment, your universe expands exponentially. Computer does not expand exponentially. So just trust me that each moment, the size which I'm showing is exponentially larger. And these hills which grow here, they are not golden hills of California. This is the distribution of the scalar field phi. This is a distribution of scalar field. So it generates, it stretches, it generates, stretches. Then the universe stops inflating. Normal universe right now takes place. So what happens is that eventually everything like cools down, the scalar field falls down to its minimum of its energy, oscillates, produces particles, and the places which were hills, they become places where galaxies form. The places which were lows, they become parts where nothing is, there's no galaxies. That's how galaxies are produced according to the theory. The places here, these are the places where quantum fluctuations are so large that the new universes, new parts of inflationary universe are being born as we speak now. Okay, so this scenario, if it is right, then it tells you that not only our universe is expanding, but once this expansion starts, in some places it's over and normal people can populate them. In some other parts of the universe, new universes are created all the time. Now, how we can prove this idea? Well, mathematically, well, everybody just looked at the calculations, did not find an error, but maybe the theory is wrong. So what do we do in this case? We go and measure. So we go, for example, to Florida, and this is a real photograph of a person in his chair in water, because it's as hot in Florida as in Madrid. Trust me on that, okay? Now, but it's also wet there. So now, this is a satellite launched. And if this person looked at the sky very, very well carefully, then he will see actually that the colors of sky, they are not totally uniform. They are slightly more hot in some places, and they are slightly colder in other places. The difference in temperature is absolutely minuscule. It's extremely difficult to find it. The difference is like 1 divided by 100,000 of a Kelvin. I mean, this is so impossible. But my experimental colleagues, see, I'm a theorist. So from my perspective, I'm giving you the whole picture. But then I'm going to my colleagues and, can you actually measure it? Say, yeah. And I say, no, it's impossible. To measure temperature, which is 10 to the minus 5 of a Kelvin, that's impossible. So they launched the satellite, and that's what they see. They actually see it in the sky. These are results of some satellite which was launched already a long time ago, about 10 years ago. In English, it's called WMAP satellite. They measured this distribution of spots on the temperature. And this is not only one experiment, many of them. Now, from their perspective, it's just spots of temperature. From my perspective, these are imprints of quantum fluctuations which were produced billions of a second after the Big Bang. They were stretched at all the sky. They modulated a little bit, changed a little bit temperature to the right and to the left. And then we look at this photographic plate, the largest photographic plate you can ever build. I like doing photography, but I'm totally humiliated by the possibility to make a photograph with the photographic plate, which is all the sky. So these people have this, all the sky, and their photograph, it shows you quantum fluctuations produced during inflation, and then frozen, and then unfrozen, producing galaxy. And why do I know that this is true? Because the distribution of these spots, red, blue, the distribution of these spots is characterized by something which is called spectrum. And these people measure, these are experimental points, these black ones are experimental points, and this red one are predictions of inflationary theory. So when 30 years ago, when this theory was invented, I never believed that it is actually possible to confirm it experimentally, because measuring temperature with this accuracy, just impossible. So now I'm just, these guys are magnificent. They're just incredible. So that's what they did. And the accuracy is growing and growing on, and new experiments are going on. And so far, so good. Nobody knows what will happen. Well, when Planck satellite, which was launched in Europe, okay, when Planck satellite will start publishing their data, what will happen? They probably cannot disprove the results obtained by previous experiments, but they may find something strange there, which will force us to change our theory a little. And we can change it a little. I hope that we will not just, dismantle all of it. But it looks like so far, 30 years of existence, so far so good. So that was inflationary theory. It is not yet a proof of multiverse. It is the proof of the basic story, what was the basis of this multiverse story. So now, these are predictions of inflation. The universe must be uniform, homogeneous, and flat. Flat means parallel lines do not intersect. And it was confirmed by observational data. Okay? The universe produces these perturbations, and they have just right spectrum, which was found also experimentally. So there are several different predictions of inflationary theory which were confirmed. So now this is just, make a moment of relaxation, because the most complicated part is still to go. So now is, now let us summarize where we are at the moment. So here is how we look at the universe. This is here, we're sitting on the Earth, and we look at the sky, and we see galaxies and we stars, and we're just observing it, and far away from us, a Big Bang. But we are observers sitting here. We are not traveling very far. So when we are looking at the universe, we use our observation like a time machine. Because when we are looking at our sun, we see the sun as it was several minutes ago. When we are looking at distant stars, we see the stars many hundred years ago. When we look at galaxies, we see the galaxies as they were shining several billion years ago. And then we look further, and we see this primordial fire created during the Big Bang. This is what these people photographed, this satellite experiment. They photographed the sky. They see these tiny inhomogeneities of temperature there. This is the maximum which we can do, or so we thought. And this is the beginning of everything, the Big Bang. Now, the new story is that what inflation tells you, that this is how it looks. There is something beyond this crystal sphere. There is something beyond this wall of fire. Because when the universe was first born, it was inflating. There was no fire yet. Fire emerged after this process of oscillation of the scalar field, creation of particles, reheating of the universe. But during stage of inflation, the universe was expanding from this size to that size with zero temperature yet. So on large scale, very, very far away from us, there is still space filled with a scalar field which is not yet oscillating, which is slowly going down, and the universe is exponentially expanding there. And if we look even further, we will find the parts of the universe where fluctuations are so large that they reproduce new parts of the universe ever and ever again. Now, when we go back, so what happened? Previously, we were like wolves. We were surrounded by fire. And at least so fairy tales tell us, that wolves do not want to go through the fire. They somehow have this instinct. They do not jump over the fire. So we were like wolves separated from inflation by this fire. We thought that everything is this part. And now we know better. Now we know that, at least we believe that we know better. Now we know that infinite universe is beyond what the satellites show us. They show us that just a tiny, very big, but tiny part of the whole multiverse. Now, here is something else. When these quantum fluctuations when they are very large. Now, first of all, we already right now established that these quantum fluctuations existed, that they were stretched, and that this was experimentally verified. So now, when we said that these quantum fluctuations existed, in the places where they are large, they can modify, well, scale of fields which exist in the universe. Like, for example, in this model, this is a model which was considered by many people like a popular theory of unification of different forces long time ago. Never mind all of these symbols, it is not important. What is important that the scale of field may be here or here or here. If it is here, then there is no difference between quarks and electrons. There is no difference between strong and electromagnetic interactions. We cannot live in this part of the universe. If we are sitting in this place, then there's totally different story, totally different laws of elementary particle physics. If we are here, then this is the universe of our type. So what happens? During inflation, quantum fluctuations bring you from one place to another, and then when inflation is over, you fall down either to this minimum and live here, or to this minimum, and then we cannot live there. Somebody else may be able to live there, but we cannot. So the universe, even if it starts with a red universe, because of the quantum fluctuations and inflation, it becomes multicolored. And this is just the final image of a set of other computer simulations which we were running some time ago. So this is a red part of the universe. This is a blue part of the universe. This is the boundary between the red and blue. There is a high wall on the boundary. So if you are in the red minimum, the distance from here to the wall is exponentially large. You will travel, this is like 10 to the degree, this number, okay? You will travel long and long and long time, and then you will come to the boundary. But instead of the custom officer, you will see the wall. And it's very difficult to penetrate the wall. But if you're young and stupid and have lots of energy, you penetrate the wall, you find yourself in the blue universe, and you die. Because in this blue universe, laws of elementary particle physics are different. Your electrons do not live there. Your protons do not live there. You do not live there. So, yes, we cannot go there and test, but that's how the universe looks like. And in some parts of the universe, laws of physics are not fixed yet. They're jumping all the time and inflating all of the time. So these high peaks, they correspond different small big bangs, which are happening all the time right now. Now, this theory was popular among some cosmologists. So we studied it with Juan Garcia Bellido somewhere in the beginning of 90s. And it was a good theory for our purposes. But not many people wanted to go this way because it's kind of too much. I remember when I was in Lebedev Physical Institute, and they wanted to promote me to the second range position, and they asked me, so what do I do now? And I told them, oh yeah, I study the theory such that, well, the particle coupling constants and the masses of electrons are different in different parts of the universe. And they looked at me like that and say, yeah. But then they promoted me anyway. So what we learned during the last 10 years, that the string theory, which is the most popular, or at least it was, or well, many people consider the best candidate for the theory of everything. We do not really know, but that certainly right now is the best that we have. Does not necessarily mean that it's true, but it's the best, so we try to find out what the consequences of this theory is. And until approximately 2003, we did not know what are consequences, because in all of these versions of the theory, our universe fundamentally was supposed to be 10-dimensional. We know that our space is 3-dimensional, and there is one time. So it's 3 plus 1 makes 4, not 10. So the string theorist will tell you, but other 6 dimensions are tiny. That's why you do not feel them. You cannot move there because the dimension is very, very small. And then we would ask, but can you explain us how they got tiny? And the answer was, well, we do not quite know, but we will probably explain it to you next year. And then continue and continue. And then people got nervous. And then eventually, in 2003, a group of 4 different people at Stanford, I was a cosmology consultant there, but there were, the names are Kachru, then Kalash. She is my wife, and she is just arriving as we speak in Madrid right now. And then me, like a cosmology consultant on the group, and there are some other professor from India, Trivedi. We found a way how to keep these 6 dimensions small. But once we found the way, other people estimated how many ways you can do it. See, these 6 dimensions, you probably can do it this way and that way. Okay, so this is the picture which illustrates the complexity of it. When you have 6-dimensional space, there are many possible topologies of this space and many different ways to organize it. And when people estimated how many is many, they come with this number. Okay, so it's a little bit less than the number which I've shown you already, but it's a huge number. And for each of this number, you have different laws of physics, low energy physics. In one of these, you have electrons, in another, you don't have electrons. In one of them, you have energy of empty space, this high, another this high. It's like having a bookshelf with this number of shelves. You have this many possibilities to have vacuum energy. Now, these people who are showing us that now this vacuum energy is not zero, they produced the number, they measured this energy of a vacuum, and it came extremely small. In all our normal numbers, if you express it in units, which are the units with which we are working, it is something like 10 to the degree minus 120. That's totally almost nothing. How they managed to measure it, just enormous ingenuity of our experimental colleagues. I'm really starting to, admire them because they're so good in what they're doing. Now, so they found this tiny thing, but why it is so tiny? And now we know the answer. Actually, in some parts of the universe, it's huge, but we cannot live there because these parts of the universe expand so fast, then they tear apart the galaxies, they tear apart human beings. We cannot live there because of the rapid expansion of the universe. In some parts, this energy of empty space is negative, and these parts collapse so fast that you cannot have any time to ask a question. And as a result, we live in the place where we can live. And this is Entropic Principle again. But now this Entropic Principle makes sense, because previously, either you are thinking about God creating one universe after another until final success. And you may think, well, how is that the God will take such a special attention to a special type of monkey? Okay, so it is kind of strange. But now what we do, we know that the universe does it itself. So if you start with tiny universe, then the universe takes care of it. And then it produces itself in all of its possible versions. So this is a picture which I used in 90s to illustrate the idea of the inflationary universe. You start with a tiny part of the space, and then it becomes exponentially large. And we can explain why it is uniform here, because you stretch all inhomogeneities. You stretch them away. You live in this expanded universe so large that you just like, well, okay, so this is something which inflation did. Now, these are quantum fluctuations which produce new and new parts of the universe. These parts of the universe produce other parts of the universe, and they all have different colors because you can jump from one vacuum to another, from one ground state to another. This idea, I expressed it in '86, which was 25 years ago. In the paper written in the journal Physics Letters, I have written that some people who study string theory, they are worried that they have so many different compactifications of string theory. And then I said, but what happens there should be considered not as a defect of the theory, but as its advantage, because it allows us to explain why we live in the universe which we live right now. I've written '86, but nobody cared about this at that time. It was too early. People at that time at the conferences, they never used Entropic Principle. They said, we never use a word in our work. A word, you know Harry Potter? Okay, so how was this? No, you never call the name of this evil person. No, you never call the name. So you never use a word in the sensible paper on Entropic Principle. We started doing it like that many years ago. And again, together with Juan Garcia Bellido, we have written papers published in respectable journals where the first part of the paper were hardcore calculations. And in the end, we would say something. And by the way, if you buy the first part of the story, this one comes free. But nobody wanted to buy this free stuff. They thought that free stuff, probably there is a cheating in advertisement. Now that string theorists, they need it. They didn't want it, but that's what they need to make the theory consistent. So this is what Alan Guth, actually the first author of inflationary theory, he said that our universe is a free lunch because you take, in his time, he thought that you need about like maybe 50 kilograms of matter to create the whole world. And then in the scenario which I suggested, you can do it much easier. Less than milligram of matter is enough to produce not one world, but infinity of worlds. And that's what I said in '83, and again, nobody cared at that time. I said that this is like a free lunch, and it's actually eternal feast where everything is served. And I can confirm it that indeed in the hotel where this foundation have put me, in the beginning when I go there, I have an experimental proof of the multiverse here, just looking at the choice of the dishes. You need to be a guest of this foundation, I guess. Okay, so one sad story about this, that all these vacuum states, all these 10 to the 500 different states, according to string theory, they're all unstable, and they're all going to collapse. So this is a sad prediction for us. If we believe the theory, our part of the universe is going to collapse. How long it typically takes for the universe to collapse? 10 to the degree, and then you write your number. Okay, so usually it's a lot. So we have many other problems which can kill us before. We can solve some problems in Europe, we can solve some problems in the United States, whatever. So we have many more urgent problems to solve. But because of inflation, eternal inflation, the universe as a whole, this growing tree of the universes, it is eternal. So it's always going to reproduce different parts. So if we cannot live there, and maybe our children cannot live there, somebody else's children in far different, distant part of the universe are going to populate the universe. And now the final question. With all of this flashy story, cannot be tested? I already gave you part of the answer in the beginning, but then so the question is, can we test it? The theory provides, so far, the only explanation as we know of the smallness of vacuum energy. People were trying to find the solution of this problem for about 30 years, even before the measurement. They were trying to explain why vacuum energy is very, very small. So now we know the solution, and this solution requires existence of multiverse. You think about something simpler, mass of the electron. If mass of the electron were 2 times larger or 2 times smaller, life, as we know it, would be impossible. If the mass of the proton and mass of the neutron, the difference between them, would be just 1% larger or smaller than it is right now, say proton would become slightly heavier than neutron. Life as we know it would be impossible. So it is really nice to believe into Entropic Principle. But we cannot make any sense out of it if we do not have choice of the universe where neutron is larger than proton and the universe where proton is heavier than neutron. Now we have lots of choices. Therefore, I consider it as experimental proof of at least this is the best explanation of many experimental data available. But then there is something else. And this something else, if anything else does not work, this is something else which I consider very important. And this is the part with which I'm going to finish my talk, even though, trust me, I can continue. But I'm going to finish with it now because this is an argument which is very important. Usually scientists say, how do I know that the theory is right? Okay, so I make a prediction and I go and check the prediction. But it is not how not only science, but in real life, it's not always how things work. For example, you go to a court and somebody is accused of killing his wife. You do not repeat the experiment. You do not give him a knife and tell, okay, here is another wife for you and we will observe. No. What you do, you try to study all possible explanations. And if all possible explanations do not work, then you hang him. Okay? So that's unfortunate, but that's how the system works. That's what Sherlock Holmes say. Whenever you eliminated the impossible, so when you eliminated alternative explanations, whatever remains, however improbable the explanation is, must be the truth. So now we have very weird picture of the universe, inflating from 1 milligram to this huge size, and then dividing itself into different universes. And then this is the way how we explain why the universe is uniform, this part that we see, why parallel lines do not intersect, why there are so many people in this auditorium, why the universe, it does not really matter whether it's cucumber or it is sphere because it's so huge. We look at this, why these spots on the sky, all of these facts, we are able to explain them. And we can explain probably the smallness of vacuum energy. And so far, we do not have a better explanation. Does it prove the theory is right? We don't know. Because I'm one of those people who created it, I am inclined to believe into it. And I remember how people asked a famous British astronomer, Martin Rees, how do you believe in this multiverse? If you would make any bets, how you would bet for reality of the multiverse? And Martin Rees, the brave person, who started believing into Entropic Principle even before inflationary theory was proposed. See, these British people, sometimes they're stubborn, they have a good idea, and they insist on it until proven wrong. So he came early to this, okay? Steve Hawking, another example. Some Russians are equally stubborn. Andrei Sakharov was a stubborn person in many, many respects, okay? So Martin Rees say, I would bet the life of my dog for the multiverse. I didn't know about it. And somebody asked me, how much would you bet for the reality of multiverse? And I said, well, I bet my life on it because this is what I'm doing all of my life. If I have something better, I would study better theory. This is my profession. This is very, very serious for me. I'm betting my life. And then Steven Weinberg, the famous Nobel laureate winner, was asked the same question. And he answered, I would easily bet the life of Martin Rees' dog and Andrei Linde. So with that, I finished the lecture. Thank you.